Welcome to the Deep Dive. Today we're tackling something truly mind-bending. Imagine this. Right at the heart of our own Milky Way galaxy, there's something 4 million times more massive than our sun. It's warping space and time so much that if you get within, say, 12 million kilometers, even light can't get out. We're talking about Sagittarius A, our local supermassive black hole.
Exactly. And SGRA is our jumping off point today. We've got this stack of your sources, articles, research papers, notes all about black holes. Our mission really is to pull out the key stuff. What are these things? How do we go from thinking they were impossible to actually, well, taking pictures of them? And, what do they tell us about the universe? It's fascinating how the scientific view shifted so dramatically from total skepticism to, well, undeniable proof.
Okay, let's unpack that skepticism first, because the story really starts back in, 1915 with Einstein. His general theory of relativity basically predicted these things could exist, these singularities, points of infinite density, and this boundary, the event horizon, where escape becomes impossible.
Right, the math pointed towards them. But here's the thing. Even Einstein pushed back. He wrote a paper in 1939 arguing they couldn't actually form in reality. He thought they were just a mathematical quirk. And Arthur Eddington, another giant of physics back then, was even more blunt. He said something like, there should be a law of nature to prevent a star behaving in this absurd way.
Absurd, yeah. So why do they exist then if even the pioneers were doubtful? What makes a star behave so absurdly?
Well, it boils down to gravity.
Yeah.
It's relentless. Stars fight against gravitational collapse using the outward pressure from nuclear fusion, burning hydrogen into helium and so on. But that fuel runs out. For really massive stars, several times the mass of our sun, eventually gravity just wins. There's no stopping it. There are these concepts, the Chandrasekhar limit, the Tolman-Oppenheimer-Volkoff limit, basically thresholds. Beyond a certain mass, even the quantum forces that support dead stars, like white dwarfs or neutron stars, they just get overwhelmed. Collapse is inevitable, right down to a singularity.
Okay, so gravity wins. But going from the math says it happens to, look, here's a picture, that's a huge leap. How do we bridge that gap?
Oh, it's an incredible story of observation. This is where it gets really concrete. We have the Event Horizon Telescope images. Okay, they're a bit fuzzy, but monumental. M87, that behemoth, 6.5 billion solar masses, and our own Sagittarius A, much smaller at about 4.3 million solar masses, but still, we imaged its shadow.
Right, and it wasn't just pictures. Didn't they track a star whipping around Sag A?
Exactly. Star S2, watching its orbit over decades provided, well, incontrovertible proof of a compact, invisible object with immense mass right there at the galactic center. That work actually won Reinhard Genzel and Andrea Ghez the Nobel Prize.
And then there were the gravitational waves, right? LIGO.
Yes. 2015, a watershed moment. LIGO detected ripples in space-time itself, caused by two black holes about 29 and 36 times the mass of the sun spiraling into each other and merging. And get this, that happened 1.3 billion light years away. The peak power output during that merger, it briefly outshone all the stars in the observable universe combined by like 50 times.
That is just insane. So these detections, they make concepts like the event horizon real, tangible things.
Absolutely. The event horizon isn't just theory anymore. We see its effects. It's that ultimate boundary. Cross it and you're cut off from the rest of the universe forever. Nothing gets back out. And inside that, the singularity. Our sources suggest it's maybe less a place and more an endpoint, the end of time even. It's where our current understanding of physics just breaks down completely.
Okay, so if you fell in,
Yeah.
what actually happens? I've heard the term spaghettification.
Ah, yes, spaghettification. Not pleasant. It comes back to John Wheeler's idea. Space-time tells matter how to move. Matter tells space-time how to curve. Black holes are extreme curvature. Near a smaller stellar mass black hole especially, the difference in gravity between your head and your feet would be enormous. The tidal forces would stretch you vertically while squeezing you horizontally, like pulling a piece of spaghetti. For an outside observer, weirdly, they'd see you seem to slow down and kind of freeze as you approach the horizon due to time dilation. But for you, you'd cross it and then, well, the stretching begins.
Right, so definitely not retrieving dropped keys then.
Definitely not.
So looking back, we've gone from Einstein thinking they're mathematical oddities, Eddington calling them absurd, to seeing their shadows and hearing their collisions across the cosmos. These absurd things are real.
They absolutely are, and they're more than just cosmic monsters. Our sources use this wonderful phrase they call black holes cosmic Rosetta Stones. By studying them, these extreme laboratories of gravity, we're learning the language of the universe at its most fundamental level. They offer, as one source puts it, a glimpse of the profoundest reason and most radiant beauty.
Cosmic Rosetta Stones, I like that.
Yeah, and it makes you wonder, doesn't it? What other deep secrets about space, time, and gravity are they still waiting to reveal to us?